Hi everyone, let's continue with session 7.7. So last time we talked about infinite intervals. That is the case when x goes to infinity. So today we're going to talk about another case for unbounded integrand where the y goes to infinity. So first let's look at the definitions of the improper integrals with an unbounded integrand. So let's see. So if f is continuous on an interval with the limit when x goes to a from the right is infinity or minus infinity, then the improper integral. So let me draw the picture. So we have a and b right here, right? A and b. And then we have a problem at a. So imagine, for example, there is a vertical asymptote here. So the function looks like that, okay? And what we're looking for? We're looking for the area under the function over the interval from a to b. And we can see a is an improper value, right? The f blows up at a. So what can we do is, because f is not defined at a, so we consider the limits. Right, we replace a by c and we let c goes to a from the right. You can see this interval from a to b, we're actually approaching a from the right. So that's why here we have the right side of limits. Okay, so that is, you gotta be careful because before when we talk about the x infinite interval, the x's either goes to infinity or minus infinity, and then we know that. But here we know the improper value is a. We also need to determine we're approaching a from the left or from the right. So it's better to draw the picture and draw the picture of the interval, and then we can figure out whether we're approaching a from the left or from the right. Okay, so next case, where if a is here, it has no problem, and the b is the improper value. So it's like we have a vertical asymptote here, then the function looks like that, right? And we want to compute the improper integrals. Well, b is the improper value, so we replace b by c, and we let c goes to b from the left. Right, so that's why this is b negative. We're approaching b from the left. Okay, so next, if f is continuous on the interval from a to c and c to b, and not maybe f is unbounded at c, then okay, what is that? So the picture is like, you know, for example, 1 over x squared, then the function looks like that, right? Okay. And then how do we evaluate, like from 0, so from minus 1 to 1, okay? We know at 0 there is a vertical asymptote. So what we can do is we can like divide it into two sub-intervals. Okay, so here we have this integral from minus 1 to 0, and then this integral is from 0 to 1. Okay, so on the left piece, we can see 0 is the improper value. So we're approaching 0 from the left. And on the second integral, we are approaching 0 from the right. Yes. Okay, so if the improper integrals has limits exist, then we say it converges. If the limit does not exist, we say the improper integral diverges. Okay, so let's do some example. Oops. Okay, so let's look at this one. First of all, it's good to figure out which one is the improper value. Okay, so for this example, we can see, do you remember what's the domain? What are the domains? So there are three, okay. So there are three functions with which is the domain, okay? So, oops, let me make it smaller. Okay. So there are three type of functions with which the domains, okay? First type, do you remember? Square root of a, okay? And we need a to be greater or equal to 0. Second, do you remember? Yes, it's fraction b over a, and we need the denominator to be not equal to 0. And the third one is ln of a. What do we need? Yes, we need a to be positive. Okay, so there are 3 types of functions with restricted domain. There are more, like tangent x, secant, but here are the 3 main types. Okay, we will see more often. Alright, so here you can see we have the denominator and we also have the square roots. So combine them. Because of the square root, we require the things inside to be greater or equal to 0. And because it's in the denominator, we require it to be not equal to 0. So that's why we get minus x squared is positive. So that means, okay, how do you solve this inequality? So we would try to make the leading coefficients to be positive. Okay, so we multiply minus 1 on both sides. Then we get x squared minus 9, because you get minus 9 plus x squared, so it's the same as x squared minus 9. And when you 0 times minus 1 is 0, but what happened with the inequality sign? Yes, we flip it. So, and then next, what do? We factor it. Do you know how to factor it? So this is x plus 3, x minus 3. Okay? So we can see, the critical points are negative 3 and 3. And how do we draw it? So negative 3 and 3, because it's less than 0, it's not like less than equal. So we don't include the critical points. And because now we have make sure the leading coefficient is positive, so that we always start with the right upper corner. And then okay, and because each of the factor, the multiplicity is 1. That is, the number of copy is 1. So we go across the x-axis. And then this is positive, this is negative, positive, this is negative. And we are looking for negative values. So we know the domain is from minus 3 to 3 and not include the endpoints. So this is the domain of this function. And we are looking for the interval from minus 3 to 3. So we can see at 3, the denominator is 0. So 3 and minus 3 are actually the improper values. Okay, so let's continue. Alright, so, okay, sorry. I go back. Okay. Alright. Okay, so first of all, we know that negative 3 and 3 are the improper value. So this is like in case 3. We want to split into 2 intervals because 0 is within the interval minus 3 to 3. Okay, so let's cut it into half. From negative 3 to 0 and from 0 to negative 3. Okay, and then because negative 3 and 3, they are the improper values. So let's say, okay, let's call this guy to be A. And then we place negative 3 by A. Okay, 0. Okay, so when we are approaching to negative 3, do we approach it from the left or from the right? You see, we're approaching it from the right. So that's why A goes to negative 3 from the right. So it's positive. And then we have dx over square root of 9 minus x squared. Okay, next we have limits. And then, okay, which one is the problem value? Yeah, the improper value is 3, right? We place it by b, and we're approaching 3 from the left. So b goes to 3 from the left of the function dx over 9 minus x squared. Okay, so now we're ready to integrate. Do you remember how to integrate this function? Okay, that is actually the trig integrals, right? Here we don't need trig substitution because we have integral for it. If you can remember, integral of a squared minus x squared dx, this is what? This is a sine of x over a plus c. What's the integral of a squared plus plus x squared? This is 1 over a at tangent of x over a plus c. Okay, so if you can remember those formulas, then you don't need trig substitution. You can just use the formula. Okay, and so now let's continue. So we have here square root of 9 minus x squared. So the 9 is like the 3 square, right? So that's why here we continue. Limit a goes to negative 3 plus, and then here we have, oops, okay, I touched it by accident. Okay, all right, so we have so this is a sine of x over, right, 9 is like 3 squared. Okay, so, and then we evaluate from a to 0. Plus the limit, b goes to 3 from the left, and then at sine of, same thing, x over a, so x over 3, evaluate from 0 to b. So what is that? We continue, so we plug in 0 first. We plug in 0, 0 over 3 is 0. Minus, we plug in a, right? A over 3, okay. Plus limit, b goes to 3, negative. And we plug in b first, right? We plug in b, then we have x sine of b over 3. Minus when we plug in 0, so it's x sine of 0. All right, so let's continue. Okay, how do we find the arc sine values? Well, arc sine is the inverse function of sine. So we first need to the sine graph, right? It passes through 0, and then here this is pi over 2. Here is minus pi over 2, right? Okay, so this is talking about, okay, the x values of the arc sine is actually the y value, corresponds to the y values of the sine. Okay, so it's talking about, okay, when the y is 0, what's the x values? Then we can see this is, the x value is 0. And here when we plug in a is negative 3, we get arc sine. So it's minus arc sine of minus 1. So that corresponds to, if the y value is minus 1, what is the x values? Well, that is negative pi over 2, right? Plus, when we plug in b is 3, then we have arc sine of 1. So it's talking about when the y value of the sine x is 1. What is the corresponding x value? That is pi over 2. And then arc sine of 0, so that corresponds to, like, if the y value is 0, what is the x value? That's also 0. So that's why we get pi over 2 plus pi over 2, that is pi. So pi is the answer of this problem. All right. Okay. So don't forget that if you have questions, you can always print screen of the steps and then email me or ask me during the online office hours. Okay. So let's look at the next one. So you can pause and try to work on this problem first. All right. Are you done? Let's go over it. Okay. So let's look at this problem. First of all, what is the improper value? Okay, 0 to 2. So 0 to 2 is like this interval, okay? Which one is the improper value? We can see what number make the denominator 0. That is when x to the 4th, okay? So here we have the denominator, so we have so x to the 4th minus 16 cannot be 0. So x to the 4th cannot be 16. So x cannot be plus or minus 2. Right? So 2 is the improper value. Okay? So we replace 2 by, let's say here, we can call it t. So usually if we have one improper value, I would call it t. If we have two improper values, like the last example, I call them a and b. Okay, so t is going to 2, and then we have 0 to t. Okay, t goes to 2 from the left or from the right. Let's look at our interval. Interval from 0 to 2, so we're approaching 2 from the left. Okay, and then we have x cubed dx over square root, 9 roots 16 minus x to the 4th. Okay, so this is like quotient. Do we have quotient rule for integrals? No. So what method do we use here? Can you see here? This is like the denominator, we have x to the 4th, and the numerator we have x cubed. So what method? Yes, u substitution. So u will let u be 16 minus x to the 4th, and then du will be minus 4x cubed dx. Right? So what's x cubed dx? It will be negative 1/4 du. Alright, so we continue. So that's the limit. T goes to 2 from the left. And then now, okay, so now we have like minus 1/4. We can put it in front. And here we have u of 0, u of t. I don't want to change the x values into u values. Let's keep it as like the x values, and then at the end we plug the x back, and then we can plug in the x values. Okay, so here we have du, and then this is over 9 roots of u. And what is that? So let's make it into the standard form. The standard form for it is u to the, because it's in the denominator, we have negative 9 roots 1 over 9 du. So how do we integrate that? So we have, we add 1 to the exponent, then it becomes what? U to the 8 over 9, right? Then we divide it by 8, multiply by 9, evaluate from u0, ut. Okay, so we continue. That's the limit. T goes to 2. From the left, negative 9. 4 times 8 is 32. U, what is u? 16 minus x to the 4th. And then to the 8 over 9. Now we get the x back, so we can plug in 0 and t. Okay, what does that mean? Well, we plug in t first. So minus 9 over 32. 16 minus t to the 4th. 8 over 9. Minus, we plug in 0, but minus negative become positive 9 over 32. When we plug in 0, we get what? 16 to the 8 over 9. Right? Okay, what happened when t goes to 2? You can see 16 minus 2 to the 4th. This guy is actually goes to 0. Okay, so that's why our answer is 9 over 32 times 16 to the 8 over 9. Okay, let me ask you a question. Can we cancel the 32 and 16 and get a 2 here? No, because 16 has an exponent 8 over 9, so we cannot cancel them. So just leave our answer like that. And because we get a number, so we can say the integral converges. Okay, and let's see, in the last problem, we also get a number, so we can say okay, I'm drawing. Okay, all right. Okay, so I want to draw. Okay, so converges. Okay. All right. So next, we're going to talk about an important theorem. Okay, so we know that there are so many integrals that we're not able to integrate and find a nice formula for it. However, we can use the comparison test to see whether they converges or diverges. So what is it about? All right, so let me change the color. Do you like pink? Okay, so let's draw it. So let's draw the picture. Okay, let's say we have a bigger function, and let's say we have smaller function. Okay. They all goes to 0 and when x goes to infinity, okay? So let's say here, okay? Let's say this is the number A. Okay, so then what is the green area? So the green area, let's say here we have the smaller function is g. Then the green area is actually the integral from a to infinity of g of x dx, right? Okay, and then how about the pink area? Okay, so let's say the bigger function is f of x, then the pink area is actually the integral from a to infinity f of x dx. Okay, so what does converges means? The improper integral. So the improper integral converges. So integral converges. That corresponds to the area is finite, right? If the integral diverges, that corresponds to the area is infinite. Okay, so let's look at this picture. The pink area is actually bigger than the green area. You can see from the picture, right? Okay, now let me ask you. Okay, if the big guy is finite, what can you say about the little guy? Okay, so think about it. Let me use a different color to emphasize. Okay, so think about it. If the big guy is finite, what can you think about the small guy? The small guy is also finite because the big guy is bigger than the small guy, right? If the big guy is finite, the small guy is finite. Okay, if the big guy is infinite, what can you say about the small guy? Well, the big guy is infinite. We have no conclusion about the small guy. It could be finite or it could be infinite, right? How about if the small guy is finite? What can we say about the big guy? Well, if the small guy is finite, the big guy is bigger than that, right? Bigger than that, it can be finite or it can be infinite, right? So, last case, if the small guy is infinite, what can you say about the big guy? Well, if the small guy is infinite, the big guy is bigger than the infinite thing, so it's also infinite. Wow, so now we can see our conclusion. If the big guy is finite, then the small guy is also finite. So that corresponds to the first one, right? If the integral from a to infinity f of x dx is convergence means the area is finite, then the small guy is also convergence, right? Okay, and next, if the small guy, right, if the integral from a to infinity of g of x dx is divergence, so the small guy is infinite, then the big guy is also infinite. So that's why we have those two conclusions. Okay? So when you think about the comparison test, you think about big guy and small guy. Which one is the big guy? Which one is the small guy? Okay? All right. So we talk about we usually use comparison test when we cannot solve some integral, but we can compare that integral to some other integral that we are able to solve. Okay? But sometimes it's hard to tell, okay, which integral we should compare with. So that's why you might need to try different functions to compare with and see which one work. Okay, so let's look at example 1. So so this is the function. We have one. Okay, let me use the black color. Okay, so we have 1 over x e to the x. What do we want to compare with? First of all, we don't know the integral of 1 over x e to the x, right? We know the integral of x times e to the x using integration by parts. But if they're in the denominator, we cannot integrate that. Okay, so what do we want to compare with that? Alright, maybe we can compare with 1 over x, right? Because we know how to integrate 1 over x. Maybe we can also compare with 1 over e to the x, right? 1 over e to the x is like e to the minus x. We can integrate that. Okay, so which one we should compare? So let's call this is the first one, this is the second one. Let's try both and see which one work. Okay, so here, which one is bigger? Well, let's figure out what's the difference. Well, the denominator are different, right? Okay, let's compare the denominators. X, e to the x, and x. Which one is bigger? Okay, what's the difference? The difference is the x are the same, right? The factor e to the x and 1 are different. Oh, which one is bigger? So remember that x is between 1 and infinity. So x goes from 1 to infinity. When the e to the x, what is e to the x looks like? Like that, right? At 0 is 1. So when x 1 to infinity, e to the x is greater than 1. So if it's greater than 1, next steps, because we multiply by x on both sides and x is positive, so the inequality will be the same. But how do we get the fractions? Well, remember, if we have a bigger denominator, then we have the smaller number. So actually, when we flip it, the inequality also flip. Okay? So that's why here, this is the big guy. This one is the small guy. And do you remember what's the integral of the big guy? So 1 over x dx. Oh, from 1 to infinity, that is like a limit. We have the improper value is infinity, so 1 to t 1 over x dx. Well, that is what's the integral of that? ln of absolute value of x evaluated from 1 to t. Alright, so that is we plug in t, right? ln of t minus we plug in 1. But when t goes to infinity, ln of t was ln of like that, right? It goes to infinity. Oh my goodness. We get a big guy is infinite. Can we say anything about the small guy? So if the big guy is infinite, can you say anything about the small guy? No. So that's why, this is not the good function that we want to compare. Okay, so oops. So we get this method doesn't work. Oops. Okay, sometimes you need to try different methods and see which one works. Okay, so don't be disappointed if some method doesn't work, because we are learning, right? Okay, next. So let's compare this guy. Okay, what's the difference? The numerator are the same, so let's compare the denominator. Okay, what is the difference? Well, we both have e to the x, so the difference is x, and this is 1. Okay, x and 1, which one is bigger? X, right? Because x is going to from 1 to infinity, so x is bigger equal to 1. So actually here bigger equal or bigger than doesn't matter, so we just need to figure out which one is the big guy, which one is the small guy. Okay, when we multiply by e to the x on both sides, because e to the x is always positive, so we still have greater equal, but when we flip it and move it in the denominator, we actually flip the inequality sign, so we have less than equal. Okay, now this is the big guy and this is the small guy. Now let's integrate from 1 to infinity e to the minus x dx. Okay, let's integrate this guy. So this is the improper integral. So the improper value is t. So we place infinity by t and set the limits t goes to infinity. And then oops. Ooh. Move. Okay. Move my dx as well. Okay. So the integral of e to the minus x is e to the minus x over minus 1, but we can put the minus here. Evaluate from 1 to t. Okay, that's the same as t goes to infinity, and then we plug in t minus when we plug in 1, so minus negative become plus e to the minus 1. Okay, now what happened? So here, see, e to the x looks like that, but when t goes to minus infinity, e to the minus t goes to, so when t goes to infinity, minus t goes to minus infinity, so e to the minus t becomes 0. Okay, so we have 0 plus e to the minus 1 is 1 over e, so we get 1 over e. Oh, see, we get the big guy. Oops. Whoa, okay. Alright. Alright, we get the big guy is finite. What can we tell about the small guy? Also finite. So this function works. So we can say our by comparison test. Okay, our integral from 1 to infinity dx x e to the x converges. Okay, so yes. So when we use the comparison test, we have to say by comparison test because it has a name, right? Okay, so that is the example 4. All right. Okay, let's continue and look at part B. All right. So first of all, we look at this and think about, okay, are we able to integrate this function? Well, what method do we use? We don't have quotient rule, right? So maybe the only thing we can try is partial fraction and use substitution. But partial fraction only works for rational functions. This is not rational functions, right? So, how about u substitution? So if we let u be the inner function 7x squared minus 6x minus 3, then du, we should expect to have some x term on the numerator, but we don't have. So it means, okay, we're not able to integrate this function. Wow, so maybe we can think about using the comparison test. So, okay, what do we want to compare with? Okay, so we have 5 over 5th roots of 7x squared minus 6x minus 3. What can we compare? Okay, I would say, what really matters is the dominant terms. So it's about the tail. Okay, when x goes to infinity, the dominant terms dominance. So dominant terms are the terms with the highest powers. So that's why we can use it to compare with. We only look at the dominant terms. So this is the dominant terms, the terms with the highest power. Okay, it's like, if you have $1 million, do you care about a penny? Maybe you do, but if you only have 10 cents, you care about the penny much more than if you have $1 million, right? So, what is this guy? We can pull out the constant outside. Okay, the constant, this is 5th root of 7. And then, okay, and then see, this is x. What is x? X to the what power? 5th root square, so 2 over 5, right? So this is the function we want to compare. Okay, let's see. What's the difference between them? Okay, the numerator are the same, the difference are the denominator, right? Actually, the difference is the things inside the 5th roots. Okay, which one is bigger? Wow, 7x squared is bigger, right? Because the left-hand side, you're going to subtract some things. So that's why this is bigger. And then when you take the 5th roots, you still preserve the inequality. But when you put it in the denominator, it actually flips. So now this guy is the big guy, and this is the small guy. Okay, so let's figure out what's the integral of the small guy. So integral from 3 to infinity of 5, 5th roots of 7, x to the 2 over 5 dx. So we can move the constant multiple out. And then this is like the we have improper integral, so we need to limit. So when you do the improper integral, you need to replace the improper value by t and then set the limits. Okay, so we have x to the negative 2/5. It's always good to make it into the standard form before you integrate when you see the power function. Okay, so this is 5 over 5th roots of 7. And then we have the limit t goes to infinity, and then the integral of x to the minus 2/5. You add 1 to the exponents. Now it becomes x to the 3/5 divided by 3 multiplied by 5, right? And then we evaluate from 3 to t. Okay, so that is 5 over 5th roots of 7. And t goes to infinity of, 5 over 3. And then t to the 3 over 5. When we plug in 3, so we have 5 over 3. And then we have 3 to the 3 over 5. Okay, when t goes to infinity, because this guy is in the numerator, it goes to infinity. So infinity minus a finite number is to infinity. Oops. So we get the small guy is infinite. What can you tell about the big guy? Well, if the small guy is infinite, the big guy is bigger than that. Well, so it must be infinite as well, right? Great. So it works. So by comparison test, we can say our integral from 3 to infinity 5 dx. This is fifth root of 7x squared minus 6x minus 3. What? Converges or diverges? Infinites. Areas infinites. It means the improper integral. Diverges. Yes. That finished the problem. Okay. Alright. So, let's continue. You can pause and try to work on this problem and follow the steps of the last problem. Okay? So once you're done, you can continue on to play the video. Okay, first of all, we can see this is quotient, no quotient rule, it's not rational function, so no partial fraction. Use substitution, the derivative of x is 7 should be x is 6, but we don't see x is 6 in the numerator. So that's why we're not able to integrate this function. So we use comparison test. Okay, what do we want to compare? The dominant terms. So consider the dominant terms of the numerator and the denominator. Okay, so what is that? So let's see, this is square root of 11 there. And then here we have x squared over x to the, this is 7 over 2, right? You need to simplify what it is. Okay, so because 7 over 2 is bigger than 2, so actually we will have more x in the denominator. And then, so we get 7 over 2 minus 2. And do you know what that is? So it's like 7 over 2 minus 4 over 2. So that's 3 over 2. Okay? Alright, which one is bigger? What's the difference? The numerator are the same. The denominator is 11x to 7 plus 4x plus 8. 11x to 7. Which one is bigger? The left-hand side, right? Because you're adding more things to it, right? And then when you put it in the square roots, that preserve inequality. But when you put it in the denominator, it actually flips. So now this guy is the big guy. And this guy is the small guy. Okay, let's integrate. So from 1 to infinity of... So the improper value is infinity. And then, 1 over square root of 11 stays there. We put it in the standard form. Okay, so 1 over square root of 11, we can actually pull it outside. And then here we have the integral of x to the minus 2/3 is x to the minus 1/2 over minus half is the same as multiply by 2, right? And we evaluate from 1 to t. Okay, what does that mean? Okay, so minus 2 we can actually pull it outside, right? And then we have the limit t goes to infinity of t to the minus half is actually the same as 1 over square root of t. And then minus, we're plugging 1 to the minus 1/2 is 1. 1 to the whatever power is 1. Okay, so now you can see what the t, square root of t is actually in the denominator. So when t goes to infinity, this guy goes to 0. Great. We have minus 2 times minus 1, which is 2. So 2 over square root of 11. Wow, we get a number. So the big guy is finite. What can you say about the small guy? Also finite. So that's why you say by comparison test, our integral square root of 11x to the 7 plus 4x plus 8 Finite means converges. Okay, so right now, let me ask you a question. Okay, so questions. We know that our integral converges. Is this guy converges? Okay, is guy equal to 2 over square root of 11? No. So we know the big guy is finite. It converges to this. The smaller guy, we know the area, the integral is less than 2 over square root of 11. But we don't know whether what's the exact value. So we only know it converges. So the answer is no. We only know it converges, but we don't know what number it converges to. Okay? We only know that this guy the value is smaller than 2 over square root of 11. But what number? We don't know. Okay? Alright, let's continue. Okay. Well, when we have power function or like polynomials, we can look at the dominant terms because the dominant term is dominant. But when we have sine and cosine, what do we do? Okay. Well, when we have sine and cosine, we use, because we don't know, we want the bigger bound or the smaller bound. So you always start with bounded between -1 and 1. Okay? So when you have sine and cosine, you always start with that. And then you see, how do you derive from like sine x to our function? Well, we add 2 to each of the term, right? Adding 2, so -1 add 2 become 1. This is 2 plus sine x. 1 plus 2 is 3, right? What's next? We divide it by x minus 1. By the way, adding a number won't change our inequality. And divided by x minus 1, because x is greater or equal to 2, so x minus 1 is positive. So that won't change our inequality as well. Okay. Yes, so now we get that. Okay, so we have 2 things to compare with. So which one works? So we know, let's try to compute them. Okay, so from 2 to infinity of 1 over x minus 1 dx. Well, that is the limit t goes infinity 2 to t 1 over x minus 1 dx. That's the limit t goes infinity. So integral of 1 over x minus 1 is ln of x minus 1, evaluated from 2 to t. So that is the limit t goes infinity. ln of t minus 1 subtracts ln of 2 minus 1 is 1. So ln of 1 is 0. So this guy is 0. But when t goes infinity, ln of t, right? Remember, ln function looks like that. It goes to infinity. So, well, this guy compared to this guy. Well, this is the small guy. If the small, so this is like the small guy. If the small guy is infinite, what can you say about the big guy? Oh, infinite, right? So good. This works. So now we have the small guy is infinite. Then we know the big guy is also infinite. So we can say by comparison test, our function, our integral 2 cosine x over x minus 1 dx also diverges. Right? So this work, we're lucky. Okay, I also want to show you what happens if we compute the other one. Okay, so we are done for this problem because we're lucky we picked a good one. Okay, so But let's see what happens if we work on the other one. So here I'm gonna do it quickly. So we have the interval from 2 to t, 3 over x minus 1 dx. Okay, and then so that is the limit t goes to infinity. Integral of that is 3 ln of x minus 1 evaluate from 2 to t. And then you can see when we plug in t, 3 ln of t minus 1 minus when we plug in 2 minus 1 is 1, ln of 1 is 0. So this guy also goes to infinity. But the problem is, this is the big guy. If the big guy is infinite, what can we say about the small guy? Well, no conclusion. So in this case, this guy this doesn't work. So we have to try another function. So that's why in this problem, this guy doesn't work, but this guy, the one on the left, this guy works. Alright, so this is the comparison test. And so we have finished all the problems in these sessions. So remember that when you have questions, you can always print screen and then email me or ask me during the online office hours. Alright, see you!